Hello, my name is Wang. I'm an assistant professor of Biostatistics at the University of South Carolina. In this presentation, I will talk about topological signal processing and inference of event-related potential response. Before I begin, I would like to acknowledge my collaborators in topological signal processing and inference. Here are a series of papers I've written with collaborators on the topic of topological signal processing and inference. We now have a complete framework for analyzing topological features in signals, and we also have some ideas as to how topological difference and indifference can be used in different contexts to highlight clinical features of interest. I will focus on methods and applications related to ERP in this talk. Here is an outline of the talk. I'll first introduce the background on topological feature extraction in signals, and an earlier permutation-based inference procedure for comparing persistence landscapes in single-trial signals. In the second part, I will go over an exact permutation test for comparing persistence landscapes in signals, followed by an application to an ERP study in post-stroke aphasia. For the last part, I will outline some work in progress that extends the framework for topological feature extraction of signals. Electroencephalography, or EEG for short, records electrical activities of the brain through electrodes typically attached to the scalp. As the oldest brain imaging modality, it is still routinely used in clinical assessment and neuroscientific studies for its high temporal resolution and flexibility of setup under various experimental paradigms. Assuming there is an underlying pattern to some observed EEG signals, we would want to recover the pattern using the observations. This is particularly relevant in an ERP study, as the signals are statistical variations of an evoked response. Classical signal processing methods typically transform signal in the time domain into another domain through, for example, Fourier and wavelet transforms. An alternative approach to signal processing has recently been advanced through topological data analysis, for which a key algorithm is persistent homology. We've set up a straightforward method to extract the topological feature from a denoised signal via persistent homology. Suppose the horizontal threshold moves upward and it hits the local minimums and maximums of the signal amplitude in the process. As the threshold hits a local minimum, a segment of time corresponding to the amplitude below the threshold is born. The segment annihilates with an older time segment as the threshold hits a local maximum of the signal amplitude. The local minimum and maximum are respectively called the birth and death times of the segment and mark the x and y coordinates of a corresponding point on the persistence diagram. The vertical drops from the points to the y=x line on the persistence diagram are collectively called a barcode. They measure how long the time segments have persisted from birth to death. Points that are further away from the y=x line in the persistence diagram have higher persistence than those closer to the line and are more likely to be features of the underlying signal. Persistence features summarize the topological evolution in the signal. We have already seen the equivalent persistence diagram and barcode, which came out with the original persistent homology paper. These features have been processed through bipartite graph matching and kernel smoothing for the purpose of statistical inference. Recently, a statistics-friendly persistence feature called persistence landscape or PL for short, was introduced by Peter Brubenik. We can use the layers of the PL directly for statistical analysis. This is our first attempt at statistical inference on persistence landscapes. The practical constraint motivating us to develop this first test is a single trial EEG dataset. By single trial, I mean there is exactly one epoch within each clinical phase of the signal to compare. In order to compare the persistence landscapes of the two phases, we had to resample the signal. However, resampling in the time domain is bound to break up waveforms with characteristic topology. So the test permutes the Fourier coefficients of the two phases of the signal and reconstructs two weighted Fourier series in the time domain with the resampled Fourier coefficients, where the distance between the PLs of two series is measured by an L2 distance. The p-value of the test is computed as the proportion of resampled L2 distances exceeding the observed L2 distance in the empirical null distribution. In practice, this test requires permutation of a large number of Fourier coefficients, which slows down the computation quite a bit. For instance, it can take up to 5 hours to run a 5-minute single trial recording sampled at 100 Hz. Also, the test requires the input signals to be single trial, so any multi-trial recordings will need to be averaged or such to be compared by the test. In the second section, I will talk about an exact permutation test for comparing persistence landscapes in the general setting. The idea here is to compare the areas under the layers of the PLs using the kamagarovsmirnoff test. This framework borrows strength from the exact topological inference approach in computing p-value exactly for the KS test, which can improve up to 1500 folds over the standard random permutation test. This framework is flexible in accommodating different applications. The user can choose to apply it to two average PLs or the two PLs of average signals, or ERPs. In improving the robustness of the test, we opted for the percentiles of the areas under the PLs of two ERPs instead of using the areas directly for comparison. Here are two simulation studies for evaluating the performance of the exact permutation test on PLs in comparison with some baseline signal tests. We see that the exact permutation test on PLs stays robust when the underlying signals are topologically similar while showing sensitivity when the signals are topologically dissimilar. The more recent application is geared towards aphasia, which is an acquired speech-language disorder commonly caused by damage to the left hemisphere, such as a stroke. Altered auditory feedback, or AAF for short, is typically used in laboratory settings to stimulate over-speech errors by externally inducing mismatch between predicted and overly detected speech. In this study, a participant vocalizes into a microphone wired to a headset under 3 pitch shift stimulus settings. No pitch shift, or with respect to speech onset, an upward pitch shift of 100 cents, and a downward pitch shift of 100 cents. EEG signals are recorded simultaneously while the participants complete the vocalization trials. Our goal is to localize EEG channels with structural differences in signals between the aphasia and control groups. Here are some examples of the ERP response down the midline channels in all three pitch shift stimulus settings. The ERP response at each channel is computed as the average over the trials of EEGs recorded at that channel under each pitch shift stimulus setting. In channel-wise comparison of average spectral powers, the result patterns were all over the place, not localizing any spatial difference between aphasic individuals and healthy controls. Here's a plot of the average persistence landscapes of the ERPs in the aphasia and control groups with respect to speech onset. Underneath the channel names are the corresponding p-values of the PL test. The most significant p-values after thresholding with a corrected 5% significance level are marked in red. We can see that the channels F2, PO3, PO4, and OZ are highlighted as topologically differing the most between aphasic individuals and healthy controls with respect to speech onset. When there is pitch shift in either direction, no channels stood out as topologically different. The dynamic thresholding process in persistent homology that yields the topological changes is called a filtration. We can remove the directionality constraints on the filtration by simply allowing an arbitrary gradient on the dynamic threshold. We refer to this filtration as the gradient filtration. By treating the signal as a smooth curve, the gradient filtration yields a sequence of arcs in its sublevel set to the right of the dynamic threshold as it moves up the vertical direction. As the threshold hits a change point of gradients on the curve, new arcs emerge and old arcs annihilate in the sublevel set, depending on the relative magnitudes of the gradients. For instance, as the threshold with a gradient of 1 hits a change point near the second smallest local minimum of the signal, the arc around it is born into the sublevel set. The filtration with respect to a horizontal threshold we saw earlier is a special case of the gradient filtration at gradient 0. A filtration value in the gradient filtration is lambda, the threshold's intercept, with the y-axis. Here is an example comparing persistence landscapes of gradient filtrations with different threshold gradients. The leftmost column consists of the sinusoidal functions on which the corresponding persistence landscapes from different gradient filtrations are generated. Again, the horizontal filtration is a special case of the gradient filtration with a gradient of 0. We can see that the magnitude of the layers differ, but the overall layer structures are largely similar. The significant topological difference between the ERPs of aphasic individuals and healthy controls in the AAF study is also confirmed by gradient filtration. Here's the result based on the gradient filtration with gradient 1. As the topological changes in a gradient filtration with a non-zero gradient is considerably more complicated, it is possible to have some missing features at some channels, such as PO3 in this case. But we still see a strong topological difference between the EEGs of the aphasia and control groups in the parietal occipital and occipital regions. Unlike the horizontal filtration, gradient filtration also shows that there is a strong topological difference in the parietal occipital and occipital regions when there is a downward pitch shift of 100 cents. There is also strong topological difference in the parietal occipital and occipital regions when there is an upward pitch shift of 100 cents. In an upcoming paper, we'll talk about how to summarize over the results across gradient filtrations, as well as signal processing settings in which the gradient filtration works better than the horizontal formulation. These methods and applications open up a new avenue for quantifying neural deficits in brain disorders through topological studies of EEG activities. The framework can be also used in other clinical settings using EEG signals, as well as studies of brain signals in other modalities such as fMRI. The fast computational implementation can be incorporated into statistical analysis of large-scale clinical EEG signals. Thank you for your attention. If you have any questions about the material covered in the talk, or would like to seek out collaborative opportunities or student projects, please email me at this address.